Cool. Hi guys, I'm Randy. This is the lecture that I'm doing today, Sprite Batching and Texture Atlases. I think this topic's pretty simple, and that's the reason why I chose it. I think it'd be really helpful for pretty much everybody in Game 200 that's, especially those who have optimization issues. I can remember when I did Game 200, we were using DirectX, and there was a lot of issues regarding specifically what's in these slides. So I believe it'll be useful. So here's a quick overview of what I'll be discussing. Do note, I'm not a graphics programmer, but I know a bit about it. So with that in mind, the discussion here is going to be focused on OpenGL, but I made it pretty generic, so it'll work with any graphics API in general. Although, as you'll see, the things that are being referenced in here are mostly OpenGL stuff, but that doesn't really matter for the content. So real quick, here's what a batch is. In general, it's just sending data to the GPU. When you do that, you can think of it like a function call, except the function that you're calling is a part of a GPU driver or API. And the two APIs that we're going to be using at the school pretty exclusively, because there's not really anything else, is OpenGL and DirectX. And usually when you hear people talking about draw calls or batching or batches, they're talking about how many times you call one of these functions here, because these are the ones that are usually used to initiate sending a bunch of data. And if you call them a lot during one frame of your game, there's going to be huge stalls because it takes there's a lot of latency between sending or initializing some data to be sent and then waiting for it to actually be used. That takes a long time. And the reason for this is because typically these APIs that you use are pretty black boxed. You don't really have any control over how they're written or what they do. They manage the GPU memory and they interface with the actual graphics hardware. And the implementation on them is usually manufacturer specific. So there's no control over it, you just use it. And there's a lot of complex stuff going on in there. And when you need to send something to the GPU, all these things that are being done for you, which are black boxed, you have no idea what's going on, takes a lot of time. That's why you want to use it as little as you can. And if you just constantly try to draw one object at a time every time your game loops each frame, that's probably going to be the biggest bottleneck in your game. And experience has shown that this is the #1 cause of performance issues in all of DigiPen games. Just using their graphics drivers or APIs poorly. So you want to use the minimal amount of batches you can during each game loop. That way you can have the best utilization of the GPU power. And this whole batch count ordeal is such a big deal that it sort of transcends all the way through the art pipeline of games. And what I mean by this is usually when art is created for a game, it's created in mind, or with the idea in mind that it needs to be packed together in a way that is friendly to send to the GPU. So you'll see things like lots of textures being packed together in atlases, which is the main topic of this lecture. So there's an idea that you can do to resolve a lot of your performance issues that you'll ever hit while at DigiPen. And the idea is to do what I call sprite batching. And the idea is that there's a limited number of textures that you can draw with a graphics API at one time. And if you take all of your images that are going to be drawn roughly around the same time and you put them on one texture, you can use different sections of that texture to draw different things. And this is called using a texture atlas. Everything's in one big texture, but you draw different sections of it for your different images. And in order to do this, there's a couple different requirements. The biggest one is the ability to sort some of your data. If you can sort your data, then usually solving this problem of batching your stuff becomes pretty simple. And of course, the result is that you'll never really have to worry about your performance issues if you do this sort of thing. So here's some rough code of what it might look like to actually batch something. For every texture in your game, you set it. You send a lot of data all at once. Usually it's just in a really big array. And then you call some sort of rendering routine. You use this data to render this single texture or sections of that single texture. So like I said, it should be very simple. And hopefully it'll feel like that by the end of the slideshow. So when you, there's a reason to sort your data, and the reason is that you need to be able to only send data to the GPU that is specific to one type of texture. Maybe you're drawing like a bunch of grass or tiles or something. You want to sort your sprites in your game so that all of them are next to each other in memory, and you can draw all of those in a big array because they're all associated with that tile or that single grass texture. And the easiest way to do this is just to use standard sort. And using standard sort is actually really simple. You provide like a single comparison function, and then you just call it. And you pass it some big array or some list or whatever, and it'll just sort your container for you. Implementing quicksort can actually be kind of, I would consider that a pretty advanced topic. So you don't actually have to implement quicksort just to optimize your game. You can use like standard quicksort, and suddenly this whole problem becomes really simple to solve. And sorting itself can be a pretty intensive task. So this is why it becomes important to make your sprite objects that are in your game a plain old data structure, or otherwise known as a pod. Have any of you guys here heard of the term pod before? Okay, like one guy. So a plain old data structure is usually a struct, and it just contains memory that's contiguous. There's no pointers that go off to heap memory or anything. Usually it's just some ints or like some floats, or maybe a string, but the idea is that it's all packed together. There's no constructor or destructor. There's no code or methods. It's just a little bit of data. So it's very simple data. And if you can have your sprite represented as this, sorting this is really easy. I'll show you an example of a sort function later, but what standard sort will pretty much do is just copy an element of your array, which is a sprite, into another spot. And it'll do that a lot. And if you just have pods, there's no pointers involved. There's nothing complex. So it doesn't matter if you copy an element and swap things around, because you're not going to corrupt your data that way. It's just integers or floats or whatever. So making your sprites pods makes this problem easy. Up here, I'll talk about this on the next slide. Whoops. I think I hit the wrong button. Here we go. So there's two different ways to send all this data to the GPU that I've been mentioning. And I want to make sure that this specific point is really clear. If anything else in this is confusing, I want this to be clear. The first way to send things to the GPU is to take your model view projection matrix and multiply it with all the vertices of all the quads of all your sprites. So that way you can output all of these transformed vertices into one big array, like a standard vector. Once you have all of these vertices that have already been transformed, you could have them in a huge array, and you send that all to the GPU all at once, and you tell it to draw it. This is the simplest way, and it's actually really efficient, even though you're performing all of these calculations on the CPU that can be done simultaneously on the GPU. Even though you do this on the CPU, it's still really fast, because it's just one draw call. And it's really simple. There's no strange indirections jumping around from pointers or anything. Usually you'll use a dynamic vertex buffer for this. My preferred method of sending data to the GPU like this is what's called buffer orphaning. I don't talk about it here, but if you're interested, you can email me after. But yeah, anyways, the point is send things to the GPU in one go. The second way is with instancing. And this is my preferred way over the last slide. It's a little more efficient because you use the GPU to do heavy computations that the CPU is not quite as fit for doing. And the idea is that instead of pre-transforming all your vertices of all your quads and putting them in an array, you have one small array of vertices on the GPU, and it's static. You create it one time, and it sits there, and it's representing a quad. So you'll have your two triangles, total of 6 vertices, and then that's it. That's That's your vertex array. And then what you can do is you can send transformations to the GPU instead of transformed vertices. So you have your quad, and you have a huge array of transformations on the GPU now. So what you do is you transform the static quad into world space and draw it. Then you transform the static quad with the next transform into world space, and you draw this. And then all of that's done on the GPU. So you're basically drawing the same texture in many different locations. And then the reason this is fast is because A, you send all the transforms once, one draw call. B, the GPU is really, really fast at performing math. So it like parallelizes the whole thing and does all these transforms like all at once. So like this is so fast that if you implement it like this just one time, you probably will never have to worry about it again as long as you're in game 200. And if you're doing a 2D game in 3D, I guess the same goes there. And a quick note, if you're familiar with shaders at all, you can do all of this in the Vertex shader. So your fragment shader is like one line long. That's how I implemented it. So like I said, the second method of instancing is my preferred way of doing this sprite batching. And if you're familiar with OpenGL, this slide will be a little bit more useful to you. If you're not familiar with OpenGL, don't worry. It's just as simple as indirect X, I'm sure. So the idea with OpenGL that I like is you can create a big texture on the GPU. And what that means is a really big array. Textures on GPUs with OpenGL are arrays. And you can put arbitrary data in them. And this is called a texture buffer object. So you make a huge array on the GPU, and then you can put transformation information into this. And the reason that I like this method is because it doesn't require any like new features that aren't on like very many platforms. Pretty much everything that I would ever be concerned with like one of my games running on would be able to create a texture like this. There's more advanced features that do like actual instancing. Like I won't talk about it, but the newer the features in OpenGL, the less likely it is to be supported on various hardware. Like if you wanted to run stuff on Edison with new features, you'll probably just have problems, and you'll have to like write workaround code and whatnot. So here's those 3 steps. The last one is after you have all these transforms in a texture, you just grab them as if you're indexing an array. So send things to GPU in an array. Those things are transforms. In the GPU, you index into the array and grab a transform the static quad into world space, and then render. So hopefully that makes sense to everybody. Is there any questions so far? Yeah, you have one?
Yeah, I've used FBO to send textures before. The texture buffer you're talking about is using an FBO in itself, or another data structure that's really called texture buffer?
When I was researching this on the internet, people were calling it a texture buffer object. That's what it was called. And then when you create one, I think the constant is GL texture buffer. I don't remember, but I have a link to some example code if you really want to see it. Okay, another thing that's usually in sprites, or 2D games with sprites, is Z-ordering. This can ensure that you draw sprites that are in the back, and ones in the front. It might sound hard, but it's really easy. And here's that example of that comparison function that I said standard sort would need. Usually, if you're just sorting by textures, you'd have this line here. You just implement a less than operator. And this can actually be like a pointer to a texture or whatever. It doesn't really matter. This is arbitrary as long as these are unique. In this case, since this is OpenGL, location would have been a handle, an integer handle. So then if you want to have Z-ordering in here as well, you just see that there's 2 different things to sort by, Z-order and texture. However, rendering things in the correct order is more important than like rendering specific textures at a time, because order makes sense to a user in your game. Trees are in the back rather than batching stuff. So this happens first. If they're not the same Z-order, you sort by Z-order. If they're the same Z-order, then you sort by texture name. And what this will do is it'll pack in your array in huge segments all of the same Z-orders into different sections of this array. And if they're the same texture as well, you'll have a section of same Z order, same texture, and then different Z order, or different texture Z order, and so on and so forth. So that way you can loop over your array, and you already know where these batches are just by seeing if the previous is the same as the next. And then you can send only like a section of this big sprite array that you sorted to instance things on the GPU. So now the talk kind of goes from batching to texture atlases. So I mentioned at the very beginning that this problem of lowering your draw calls and your batch counts transcends through the art pipeline. This is one example of that. Usually you'll see this sort of thing happen in a lot of games. And this is what's called a texture atlas. Or at least, this is an image that is being used by a texture atlas. And the idea is you put all your images in one texture, like one PNG file, for example. That way, whenever you render any of these things, they can all be in the same draw call because they're all in the same texture. So if you wanted to use texture atlases, there's some free tools on the internet. Usually they're GUI based. So like you open a window and you pick which images you want to be like clumped together, and then it outputs one file. GUI based stuff like this, although nice for people that don't know programming, is pretty like slow and rigid. Every single time you make some images, you're gonna have to go like open this window and like do stuff by hand, and it's manual labor. If you make your own tool that can make an atlas, then you can run it from the command line. So like your program can just like automate this stuff, so you don't have to open and manually do things. So I recommend doing something from the command line. So I'm going to go over how to make an atlas generator real quick. And the idea is you load a bunch of images from a file. Usually you'll handpick these images because you think they'll be drawn around the same time. Then you place them all into one huge image. You save it, and then you save an atlas. And I'll talk about what that is in a bit. So here's the actual atlas. The idea is that you want to map the old image name to UV coordinates. And that's it. Usually you can represent UV coordinates as an AABB with the min and max vector. If you have an AABB like this, min, max, 2 points. So here's an example of, you can imagine like these different squares as different images in a texture atlas. This is a problem that you can call bin packing. Bin packing is actually pretty well explored, and it's what's called an NP hard problem. I don't remember what NP stands for, but I read the Wikipedia page a while ago, and I don't honestly remember what it means. It means it's a hard problem to solve, and you can't just explicitly write an algorithm to just compute the answer. You have to use some sort of like search heuristic or do some approximation. So I'll go over the simplest algorithm I could think of to like make a texture atlas. So you start with a big array, 2D array. This is just a bunch of empty pixels. You just allocate a bunch of space. And you want to put smaller images inside this thing. So here's the empty space. Then you place an image into a corner. And you're going to place images in the same corner from here on out. It doesn't matter which one. We're just going to keep it consistent, that corner. So now we need to somehow partition this empty space into more squares, or not squares, AABBs, rectangles. And the way I chose was to pick the smallest extent of this image and partition that. And by extent, I mean is the height or width smaller? In this case, the height is smaller, so I partitioned that. Now I have two spaces, two empty spaces. So I'm going to go ahead and place another bin in here, and I'm going to pick, that's the bin that was placed. I'm going to use a best fit search. I'm going to find the empty partition that is the smallest that I can fit this new image in. It was that one at the bottom. So now I place it at that location and do the partition step again. Which extent is smaller here, x or y? Clearly the x is smaller, so I partition that slot right there. And this just goes on until you're done and you put all your images in here. And you'll have some arbitrary partitions, but you'll get a pretty good, efficient use of your space, and the algorithm is really simple. So if you were to implement this, this might be what your partition looks like. You can have a linked list of AABVs representing empty spaces. And when you do your best fit, you can loop over your linked list and just keep track of whichever partition is smallest that your image can fit in. And then when you're done searching, an O of n search, you return that best fit, and then you stick your next image in there, and then just repeat the partitioning step until you're done. So the only hard part about this algorithm, I think, is like how to do this partition step. So I drew it out on paper and came up with this. When you're placing an AABB into your space, after you figure out which extent is smallest, in this case it's that one, what you have to do is you have to somehow split this huge partition into two smaller ones. So what I did was, first, I make a small new one, which is going to have a width of that small extent and a height of the difference between that and the old partition, that as in the small image. So making this AABB should be pretty simple. And then you take that width and you modify the old partition by the width. So you only have to make one new one instead of making two and deleting the old one. So I think that's pretty simple, and I think you guys can figure out the rest from here. So let's move on to concluding the lecture. Here's what an actual Atlas file might look like. This is one I made, and I'm using this in one of my projects right now. It just has two images which were originally separate PNG files. However, now they're in one texture, or one PNG file, which is loaded as one texture. And here's what the atlas looks like. It maps the old PNG name to UV coordinates. Oh, and I guess I forgot to ask if you guys are all familiar with UV. Who doesn't know what a UV coordinate is? Cool, you all know, so I can just skip that. I mentioned a while ago that if you're going to make a tool, you should make it command line based. And this is why. You can use a system call in C code to call to open your executable, and this is your tool, your Atlas generator tool. And then you can pass it command line arguments. And this is an example of the style of command line arguments I use. So this is where I want my output file, my output atlas. That was my output image with everything packed into it. That's the X and Y width and height for my new atlas, and then that's just with the folder of where I wanted it to go. So command line is good because you can have code run your tool rather than you manually clicking on stuff, this is of course more time efficient. And then here's a couple quick notes in case you guys care about making atlases during runtime. For more complex stuff like 3D rendering and whatnot, oftentimes you're generating things called light maps or other stuff during runtime, and you need to render these efficiently. So you can, during runtime, make a texture atlas in memory, but you want it to be fast. So you can use a tree query, binary space partition, instead of doing that O of n best fit search. And then, of course, you can use locality of reference to make sure that all of these partition nodes in your linked list are all actually elements in an array. And instead of pointers for next and previous, you can use array indices. That's about as fast as you can make this thing that I'm aware of. But of course, that's for probably more advanced junior year stuff if you're doing a lot of lighting and whatnot. The last thing is a quick note on premultiplied alpha. Alpha transparency is when part of an image is see-through. Traditional alpha transparency makes it so that if you have a half transparent image, you can see half of the background behind it. And that's usually what you see in Photoshop when you just start erasing stuff with a brush that has some transparency in it. However, there's another lighting technique called additive blending. So remember those two, that red and that orange circle I had in that really tiny atlas? Well, I'm rendering a lot of those red and orange circles with additive blending. And instead of overwriting the colors directly, they add together. And of course, if you add a bunch of numbers together that are between 0 and 1, you're going to result in 1, which is white. So I'm just rendering a bunch of little circles, but it looks like a cool fire. So the whole point of Premultiplied Alpha is so that you can do traditional alpha and additive blending without switching render states. And usually, like if you're using ancient techniques, if you wanted to do traditional alpha and then additive, you have to do a render state switch. You have to tell the GPU, do alpha this way, now do alpha that way. And when you switch, that's kind of like a batch or a draw call, as in it's slow. But if you do use this technique, you don't have to make a switch. And the idea is that when you load your image, you take the alpha part of your RGB A pixel, and you multiply the RGB part by the A. And then you render stuff with a slightly different interpolation of the alpha. And if you want to know like the specifics of how to do this, it's in the source code I link on the next slide. But the cool thing is that if you have 0 alpha on a pixel, it means additive blending. There's the link to all the example code for everything in the slides. You can look at it if you want. You don't have to, though, of course. So then again, here's a final product of a really efficient like particle effect that doesn't take any artistic skills whatsoever, unless you're so artistically terrible that you can't draw a dot. But anyway, this actually, yeah, that was the last slide. So this brings us to the end. Are there any questions about like anything that I went over? Don't be shy. Yeah, you have one.
In your Atlas thing, you had like floating point numbers for the coordinates. How come they weren't like just like pixels?
Oh, so these are UV coordinates. So the way UV coordinates work is they represent a range of 0 to 1 on the x-axis and 0 to 1 on the y-axis, at least for OpenGL. So your coordinate system is like this: x, y, origin. And you multiply these normalized floats by the amount of pixels to index into a specific pixel and grab it. And the reason that you store these UV coordinates as 0s and 1s is so that, well, it's so that it's normalized. This can be like scaled arbitrarily, and you don't have to like hard code the widths of all these different images in here. So the way to read this would be for the orange ball, the bottom left. Oh, whoops, this is red. The bottom left UV coordinate would be here, and the top left would be all the way to the right, and then up by half of the image. So min and max. And then, of course, this one starts halfway up and goes all the way to the top. So that's how that works. These things are just sectioning off your big image to know like which parts to draw, depending on what image you want inside of your atlas. Yeah, good question. Any others? Yeah, you have one?
When you apply the BuzzFeed, won't you have a problem with fragmentation? Like
Yeah.
perhaps you have this last image that you have enough space technically, but because of the way BuzzFeed organized, one part is here, another is here. How can you deal with that?
So the question was, when you're doing the best fit algorithm, how do you deal with like space fragmentation? Well, the first step is to do something kind of smart. Best fit is kind of smart. If you just choose a random partition, then you might not get a very like intelligent pick. You might pick like a partition that's super skinny or something, and then you get a lot of wasted space, right? So that's the first step. Second step is to always go into a specific corner. So that way you're trying to fill up one portion of your atlas first before going to the rest. The next step that I didn't spend an infinite amount of time thinking about this. There's more you can do. But this is the last one I know of from my limited research is you sort your sprites from smallest to greatest depending on surface area. And when you insert things into the atlas, you insert starting with the greatest one, the biggest one. Because if you start with inserting like a bunch of small ones, you get a lot of different partitions. if you start with the biggest one, you take up the largest amount of surface area with the least amount of partition. Does that make sense? And usually the smaller ones at the end of your list will fit into the spaces of the bigger ones. Also, the heuristic that you want to do when you're doing your best fit is based on surface area, because you can imagine a really, really skinny rectangle with hardly any volume is going to take up a lot of space in this, this atlas. Because if you just want to add a big square, you can't, because you just took up half of your image and partitioned it kind of arbitrarily. So if you go by small volume, you can get weird cases like that. If you go by small surface area, then it'll actually prioritize properly. So those are the ways I know of fighting fragmentation. But you'll always have some, because like I said in the original slide, it's a hard problem to solve. You're not going to do it perfectly. Any other questions? Yeah, Tony had one.
Yeah. Why is the additive blending if it's 0 alpha? Is that kind of an arbitrary?
No, okay, so the question was, why is 0 blending for pre-multiplied alpha mean additive blending? And the reason is because if you look at the way alpha is introduced into color, like the equation for it, it's just simple interpolation. But if you write the math out, you're doing traditional alpha blending, except if you look at the mathematical formula for the case with a 0, it's the same formula as additive blending. So it's a mathematical simplification, is why that is. You had a question?
Yeah. How big can you make a texture, like presenting it to the GPU?
You can make it pretty dang big. Like I think Zero Engine default atlas size is 1024 by 1024 pixels. And I've seen like their atlas have half of it empty. So yeah. Cool. Any others? All right, that brings us to the end.